I am going to invite us. Now, this is simulation, so not worry about that. This is ChatGPT running 4.0, and we run a very simple prompt to it, which looks into generating a nice image. Maybe you can see this, of Cannes, which is really, really far from reality if you have seen the seaside of Cannes. But it nevertheless gives us a particular action, and we are going to double click on. So follow me all the way through. So this prompt, just one single prompt, costs one full phone charge of your biggest iPhone 16 Pro Max. I don't know if it means anything to you, but it takes roughly on your bed, next to your bed, about 12 hours to fully charge an iPhone, on a regular charger. Now, what it means in terms of actual energy cost, well, it's relatively small. It's only 0.0029 kilowatts per hour. And we have also consumed 500 meters of water to cool down the very server, the GPU, that has been used to respond to this prompt. Okay? That's not that much. But let's take that to the scale of what ChatGPT is today. This data, by the way, comes from ChatGPT, so we haven't made this up. So there are roughly 300 million people who are users of ChatGPT. That number keeps growing every day. This obviously is the most popular GPT in our focus these days, but it's not the only one. If we assume just 10% of this 300 million people using ChatGPT, doing the same prompt or similar prompt that we have just done, it equates to 87,000 kilowatts. So in other words, 87 megawatts. That sounds interesting. We are talking about just one day of usage of ChatGPT across just one prompt. And it corresponds to 15 million liters of water that's consumed to cool down all the GPUs that have just served these users throughout the day. It's very hard to get these numbers and interpret them in the way we can see its impact. So I'm going to attempt with you something hopefully you're going to find interesting. Tesla Cybertruck. I think it's the ugliest car of the universe. But it's my taste. And I was in California just a few weeks ago. There were plenty of them. There's a Cybertruck driving there. But the reason I picked this car is because it's going to be units. We're going to start measuring this energy consumption of ChatGPT against, both in terms of its energy consumption as well as physical space. 122 kilowatt is the battery size of a Cybertruck. It has, I think, a good 800 kilometers range. So it's a pretty good driving capacity. And if I were to divide that number that we had just seen in the previous slide in terms of number of megawatt hours it would consume for a single probe inference, that corresponds to power of 9,395 batteries of a Cybertruck. Now we are starting to see the measure, the size, the impact of what it means to run those parks every day. And as you know, that number keeps going up as more adoption is coming every day into our day-to-day lives. And we are only talking about here in just one program. This is not Gemini, this is not Llama, this is not DeepSeek, this is its Anthropic, etc., etc. So let's continue this journey and see where it leads us. I thought another physical representation other than just the number of trucks will be an interesting way of comparison. and we just looked at the dimensions of a Cybertruck and mapped that to the most popular sport here in Europe, football. That is 60 terrains of football in size. So that means that if I were to take these cars and put them next to each other, this 9,300 and change will occupy 16 terrains of football. We are starting to see the size of it. Now you may wonder, why is he comparing to football size? Well, large data centers are millions of square meters. And that number keeps increasing on the planet pretty much every other month as we are adding more and more capacity to sustain the increasing growth in usage. So this was just prompt for one day, for just one program, for just 10% of its population. Now, imagine we had to train this model. Now, unfortunately, I have not been able to get a traceable and verifiable data around training ChatGPT 4.0. Wasn't available. ChatGPT wouldn't tell me the answer. So I had to go into what I could gather was ChatGPT 3. So this is at least 2 generations before. Well, back then, so that means that the last 3 years ago, when OpenAI started training their program, it took them 18 football fields, equivalent in size of Cybertrucks, of 10,900, so let's say 11,000. I think it's safe to assume that these days, the new programs that are going to dominate the next generation of inference and prompting are going into hundreds of thousands of GPUs, not in 50,000 or 100,000, but hundreds of thousands. I was talking the other day to Mark Zuckerberg, and he said that what is very interesting in fundamental model learning is that we have yet to find the asymptote at which we start getting diminishing returns for the number of GPUs we put in a network. So in other words, it is a linear progression with no end in sight. The more GPUs you add, the more GPUs you can up, and the more the program gets better. And that's the reason why the top 5, 6 companies dominating the world of AI are on a race to grab as many GPUs as possible, as powerful as possible, create as high density as possible, in order to make sure that they can train their models faster than their competitors, but at the cost of what? That is what is at stake. And if there's one key takeaway here, is that we need to be cognizant that this revolution that we are very much the actors of has dire and direct consequences in the way we are going to live tomorrow. So I wanted to take this concept one step further. You remember that was the image generated by the prompt, pretty lousy one, you'll agree with me. At least we'd have taken the internet picture, but didn't. This is supposed to be the city of Cannes. I asked the team, hey, how many megawatts we consume in this lovely city of Cannes? Cannes has roughly 75,000 inhabitants. In summer, it goes to 300,000. Don't come here in August. I'm telling you here, with somebody who you see. So we are talking about roughly 215,000 megawatts of energy consumed in the city of Cannes today, for about 75,000 to 300,000, very thanks to these facilities. And now let's compare the size of Cannes in energy consumption to the size of energy consumption of ChatGPT. So what it takes in 1 year for the city of Cannes to consume its electrical budget, it is consumed on these conservative assumptions in just 2 months. So in 62 days, that energy is already consumed. And again, this is just one program, not the whole world of AI. I was really too scared to do the map for everything because I want you guys to walk away from this hopeful and not fearful. So what is going to happen with all of that? And the quick math shows that it's 5.8 Kani there. So I was at Élysée, which is the French presidential palace, the White House of France. This regard to this picture, and there was the former CEO of Google, Eric Schmidt, was on stage like I am today with you. And somebody in the back raised his hand and asked the following question. Well, this is all good, but is there a better way? Is there a different way we can power all this capacity to compute for AI, to help AI train better? We have gazillions devices that exist already in the world, roughly 10 billion, it's growing very, very fast. Why can't we use, what is it that makes it, not workable? His answer, Eric Schmidt, I cut it very short, it's impossible. It's been tried before, it doesn't work. Well, we are going to try to prove him wrong together right now. And here is why. We are going to the core of what we just talked about, the graphic processing unit, the GPU. You might think that is the atomic entity of computation for a particular instruction that is running this particular prompt. I'll get one more time technical, that's it after that. And therefore, this particular unit is atomic in itself, and all it does is taking one instruction and continuous instruction and sending back its result. But if we double click into this particular chip, what we see is something quite different. Actually, within the GPU, there are hundreds of processing units. The bigger the GPU size in its model, the more cores there is in a particular GPU. So what a GPU does, it shrinks distance. It takes processing units, brings them together into a 5 nanometer, 4 nanometer space, groups them all together in order to deliver a distributed computational capacity within that particular GPU. And through that, we have the impression, when we look at the GPU itself, that it is just one instruction, but it is not. It is actually doing parallelized distributed computing within this particular unit of computing, which actually is exactly the same on a central processing unit, what you have in your qubits. We have moved away from single instructions long time ago. And now all of the processing units have within themselves distributed computing embedded. Now we are getting into something interesting. If there is the case, why is that we can't take the devices that you have in your pockets, you have home, in your office, and make them participate into a computational community to deliver that prompt and do it far more efficiently than going and creating these mega and giant data centers? Why is that? Why can't we do that? Well, first of all, the technology underlying that connected tissue of distributed computing is the same whether you are running on a 1 square centimeter or you are running at 1 million square centimeter. What I'm talking about? Well, somebody has to take work
and cut it in small pieces. GPUs do that. But if you take it to a big scale, but you need the software that takes an amount of work, distribute it in small pieces. And then you need something that's going to take those small pieces and show it here and there and make sure that they run their programs to deliver the result they want. So that's where we are distributed computing. Same thing happens in a CPU, in a GPU, and same thing could happen here. Okay? What do we need to after that? Well, we now have results. We have computational results that we need to bring together. So then there is a reassembly machine that comes back and puts all these things together, weights the result from other devices that are running in order to bring this result to the workload manager, say, I finished my result after n number of computations. That's what the GPU does. And that's exactly what we could do in a distributed computing infrastructure. But we have not been able to do that, don't we? Now, there has been a number of challenges all the way, I'm going to say, the last 5 years. If you go back just 10 years ago, the speed of connectivity, which is the essence that we gain by creating a very high density chip at a 4 nanometer range, taking it out to distributed computing has been a challenge because we just don't have the symmetry and the bandwidth capable of processing data fast enough. And so people had to rely on high density centralized infrastructures, because otherwise you'll have to wait way too long. And we humans are impatient and we want things to go fast. So we had to resort to this. But the last 10 years have seen a massive, massive change in the way computers are interconnected with each other. We are now talking about 100 gigabit connections per second. We were at one just 2 years ago. And you know, what is the limiting factor of a server that's running a GPU? It's not the GPU itself. It's actually the network that connects that particular server to the other server that needs to work together. And so, as devices get more powerful, as network speeds get more and more faster, the limitations that have prevented the world to shrink, to compute these days within this 10 billion device community is changing. And I want to show you a few examples of that. How many of you own cryptocurrency? Raise your hand. Good. You guys are going to lose money? No, sorry. I'm only. Well, these numbers are just from a couple of days ago. This is a number of transactions that happen daily on blockchain, at different blockchains. And those who have a little bit of experience with blockchain is the illustration, and actually is a perfect illustration of distributed, decentralized computing infrastructure. Like, I would say it's one of the best publicly known today. Prior to that, a company I used to work for, Skype, it was, you may remember, whoever ever used Skype? Arno, thank you. Had 500 million users. And the entire Skype was based on peer-to-peer technologies. So we know how to make this thing work, even when the network sucks. There's another application that some of you might use every day. That is Spotify. For those who do not know, Spotify is a perfect illustration of a hybrid model. About 90% of Spotify is peer-to-peer. So when you go on your Spotify and you want to download a song, right? Or you heard the song name. So what Spotify does, it goes to a centralized hash table, database, address book, and says, where I'm going to find this song? Tell me, where is that tab? And it doesn't say, hey, it is in my database, here, grab it and send it there. No, it actually is here, and there. So it finds the nodes next to me who actually have this piece of data that I am just querying about. And not only it does that,
but it starts already downloading these pieces from different phones and computers that exist, so that when I hit play, this is something called time to first byte of information, happens in less than 200 milliseconds. And that could not be made possible in a centralized infrastructure, because just a round trip back and forth to whatever server it is impossible to meet within that timeline. So it's another perfect illustration of distributed computing right in our pocket that we use every day. There is another attempt which actually is working nicely today, which is what we've been doing with Hivenet. 2.5 years ago, we took on the challenge to create the world's largest distributed storage infrastructure, but not by using data center hard drives, but using contribution from individuals all around the world and bringing them together in a community through which they can participate and they can share storage in exchange of storing their own personal files and pictures and etc. And I'm very pleased to announce that in the last 13, 14 months that we've been live, we've stored over 1.4 billion blocks. And every week that network grows by 5%. And we simply don't see the limit. We have 195 countries, people contributing from all over the world, and we are adding contributors every day. And it is entirely run in computer-to-peer. So I'm convinced that there is a better solution. I decided to give you a taste of what it means to run this particular prompt now on this infrastructure. This is actual data. We are now running on a stick infrastructure of devices. The same prompt. With Hivenet, it is 50% less energy consumed and exactly 0 liter of water. Same prompt. Now, you remember what Eric Schmidt said? Impossible? I don't know what you think after this short demonstration, but I think impossible is an opinion and not a fact. With that, ladies and gentlemen, thank you very much.